Hi everyone, this video is going to be just a one-page summary of everything we've done so far in section 3.1, just to make sure we've got all the major concepts down pretty well. So we're going to start off, right? A derivative is just the slope of a curve at a specific point. Okay, and what I want to add here, so when we're talking about the derivative at a point, that's the same thing as the slope of the tangent at a point, or the instantaneous rate of change. All those things mean the same thing. So I want to make sure we keep kind of coming back to that idea. Derivative at a point is equal to the slope of the tangent at that point, which is equal to the instantaneous rate of change at that point. So by now we've got a few ways that we can find the value of our derivative. And so first we're going to take a look when we're looking at the derivative at a specific x value. So in last section we learned a new form. I'm just going to use the function f of x equals x squared, and I want to take the derivative at x equals 2. So our new form to find, I'm going to call it f prime of 2. We know that's the derivative of f when x equals 2. We have a form that looks like this. The limit as x approaches 2 of f of x minus f of 2 over x minus 2. And so we can go and we can simplify. We know f of x is x squared, f of 2 is 4, and then we have x minus 2 in the bottom. And I know I can simplify this by factoring my numerator and then canceling that factor from the top and bottom. So my limit is just the limit as x approaches 2 of x plus 2 or 4. So that is equal to the value of f prime of 2, the derivative of that function at x equals 2. Now, just for the sake of review, we could also do this with our general form. If you remember in Chapter 2, we also knew how to find this value. We didn't call it the derivative then, we called it the slope of the tangent. But we could also find that by using the limit as h approaches 0 of f of x plus h, but since we're x equals 2, we're going to do f of 2 plus h minus f of 2 over h. And so we can work that math. We have 2 plus h now, quantity squared, minus 4 all over h. So if I expand that, I get 4 plus 4h plus h squared minus 4 all over h. And when we simplify, this simplifies to 4 plus h. So now if I take the limit as h approaches 0 of 4 plus h, my limit, or my derivative, is 4. So we need to be able to recognize both of those forms, but either one will get you the same answer. Now, when we're talking about the general derivative, we're just saying that we want to find the derivative of our function at any point x. So we want a general formula that we can use to find the value of the derivative at any x value. So here, if I just want f prime of x, I'm going to use my general formula. The limit as h approaches 0 of f of x plus h minus f of x all over h. And so now I'm going to substitute x plus h everywhere I have x. So x plus h quantity squared minus x squared over h. X squared plus 2hx plus h squared. I subtract my x squared term, and that's all over h. And so now I can simplify by canceling my x squareds, and I can factor an h out of each of these terms. So I get 2x plus h. So now I'm going to take the limit. This is all equal to the limit as h approaches 0 of 2x plus h. And if I substitute 0 for h, I know that my general derivative, f prime of x, is equal to 2x. So that's how we find the derivative at a specific x value, and also a formula for our general derivative. So the second piece of this then was connecting up the graph of a function with the graph of its derivative. So a quick review on this point here. Remember we said that maximum and minimums on our original function, right, become the zeros on the graph of the derivative. So here is my function y, and this graph is y prime. So where my max and mins occurred on y, those are the zeros of the graph of the derivative. Now, if I look on my original function y, wherever I have a positive slope, so over this interval and this interval, we notice that my derivative over those same intervals is above the x-axis. So positive slopes on original equals above the x-axis on the derivative. And then wherever I have negative slopes on my original function corresponds to my derivative being below, and I'm just roughly doing this, I know, but I'm below the x-axis on the graph of my derivative. So those are the major concepts that I want you to be taking away from section 3.1.